Hello everyone. So today I'm going to show you an example of a pumping system where in this system we have a pump that is used to transfer the fluid from tank A to tank B. All right. So the fluid here is water with 9.810 kilonewton per meter cube of the specific weight, and the vapor pressure is 2 kilopascal in absolute. All right. So the question asks you to draw a system curve onto a performance chart or a pump performance chart given. So the chart is given at the bottom. And from the chart, you need to determine the pump impeller size and the pump efficiency. So to draw the system curve, you need to have an equation. So the equation is HP equals to a constant plus another constant times Q squared. Because on the graph or on the chart, if you look at the chart, there's a x-axis um, with Q, which is the flow rate in liter per second. And then the y-axis is the total head in meters. And on the chart, you can obtain the efficiency of the pump, the power, the MPSH required, and the impeller size. All right. So you need to get the equation in of HP equals to a constant A plus K times Q squared. So to get this equation, uh, we can actually draw, you can actually use or apply the steady flow energy equation. So in the steady flow energy equation, we have to have 2 points. So the 2 points that I select here is the first point is on the water surface of tank A. Another point is at the water surface of tank B. Because it's already given here that the elevation of point 1 and elevation of point 2, there's a difference of 30 meters. All right. So for point 1, for in the SFEE or steady flow energy equation, we have pressure head and velocity head. We have elevation head and the head supplied by the pump, HP. It's equal to P2 divided by gamma, which is the pressure head at point 2, velocity head at point 2, and elevation head at point 2 plus. So here we have HL. So HL is basically the head losses in the system. So HL consists of major loss and minor loss. So major loss is due to friction in the pipe and is given by a summation of FL over D V squared over 2G, where F is the friction factor in the pipe, L is the length of the pipe, D is the diameter of the pipe, and V is the velocity of in the pipe. And plus a summation. So the minor losses is due to the components. For example, we have elbow, okay? Elbow, or we have the valve and the inlet and the outlet. So there will be losses in these components. So the minor loss is the summation of KL, where KL is the loss coefficient in these components, times with V squared over 2G. All right. So, so what is P1? So P1, since the tank is open to the atmosphere, so P1 is atmospheric pressure. Similarly for P2, it's at atmospheric pressure. And the tank is open to the atmosphere, and we assume both tanks um, are very large. So velocity is almost zero on the water surface. All right. So we can actually cancel P1 and P2 because it's the same value, PATM. V1 and V2 because the velocity is almost zero and in a large tank. So what we have here now is HP equals to Z2 minus Z1 plus, all right, for the major and minor losses, you have to look at the diagram. Okay, in the diagram, we have um, the pipe before the pump. We call this pipe as suction pipe. All right. And after the pump, we call this pipe as discharge pipe. So in the suction pipe, the values for the length is 20 meters, diameter is 20 centimeters. Friction factor is given there, and the KL, we have K1 and K2. While for discharge pipe, the length is 100 meters, diameter is 10 centimeters. This is the friction factor and the loss coefficient on the pipe. So you need to replace into the equation. So plus F. So I put a subscript of S for the suction pipe. So Fs times Ls divided by ds Vs squared over 2G. Okay, since we also have KL, so I put together, I put in bracket plus K1 and K2 is the loss coefficient in suction pipe. So times with Vs squared over 2G. And I continue at the bottom here for discharge pipe, we have F D LD divided by DD VD. So we put in the bracket because we also have minor losses with K3, K4, K5, K6, and K7 for this question. If you have more or you have less, so you have to follow the diagram. All right. The components. So VD times VD squared over 2G. Okay. So all the values for F, L, D, K, and Z2 minus Z1, we already have. It's just that Vs, we don't want the equation to have V or velocity because we want the equation to be in terms of Q. So we can replace V with Q by using Q equals to AV. So Q equals to AV. Therefore, Vs is Q divided by A, where A is the cross-sectional area, pi d squared over 4. So Vs is Q divided by A is 4Q over pi d squared. All right. So 4Q divided by pi ds is 20 centimeters. Convert to meters. So you should get this. Please calculate. So you should get this as 331.831 Q. All right. So Vs, in the equation we want Vs squared over 2G. So we just square everything with square everything. Then you divide by 2G. So you should get 51. Please calculate 51.642 Q squared. So you do the same thing with VD. So VD is basically 4Q divided by pi DD squared. So DD is 10 centimeters, convert to meter. So this you get 127.324 Q. And we want VD squared over 2G. So you just square everything. You divide with 2g. So you should get this 826.269 q squared. So this should be the component for suction pipe, and uh this is the sorry, not that one, not this one. So this is the component for suction pipe, this one, and this is the component for discharge pipe. All right, so you replace into the equation, this equation, the HP, the long equation. So HP equals to Z2 minus Z1 is already given there, 30. Okay, 30 plus, so F, you look at the table, F is 0.0164, length is 20 divided by 0.2 diameter, and then plus K1 0.5 plus K2 0.26. So everything here has to times with V2 or Vs squared over 2G, which is 51 point. I write it nicely here. So 51.642 Q squared. All right. And then we also have the discharge pipe components. So 0.0150 is the F. The length is 100. The diameter is 0.1 plus. So K3, 0.26. K4 and 5, we have 0.3. And then we have 2.1 for K6 and 1 for K7. So everything here you times with 826.269 Q squared. Okay, remember you calculate for suction pipe and discharge pipe separately, because later you need to use it for question B. One of them you need to use it for question B, which is for the suction pipe. All right. So 30 HP equals to 30 plus. So what do we get here? You calculate. Please calculate. So you should get 123.941 Q squared plus 15666.060 point Q squared. All right. This is for discharge pipe and this is for suction pipe. Then only you add them up. So therefore, HP equals to 30 plus 15790. Actually, if you don't write 0.001 also okay. But this value is in meter cube per second. So if you look at your chart, the Q is in liter per second. So how do you convert this to liter per second? So you just write 1000 liters is basically 1 meter cube. So if you want 1 liter per second, you just basically have to divide by 1000. But since your Q here is squared, so you have to square all with 2. Therefore, so I write it here, HP equals to 30 plus 15790.001 Q squared. You divide by 1000 squared. You will get 30 plus 0.01579. So I take 4 significant figures. So this equation is in liter per second. So now it is in liter per second. All right. So once we have the graph, we should be able to draw it in or to plot the points. So we draw a table with two columns where the first column is for Q in liter per second and another column is HP in meters. All right. So if Q is 0, of course the HP is 30. And then you need to calculate if Q is, so I choose 10, 20, 30, 40, 50. Because if you look at the graph, the number is on the scale. So 0, 10, 20. So I put 10, so HP will be 31.6. If Q is 20, your HP is 36.3. If Q is 30, your HP is 44.2. If Q is 40, your HP is 55.3. And last but not least is if Q is 50, your HP is 69.5. So I stop here because on the graph, the maximum HP is 70. But if your graph has more than that, you can actually add more points. So I plot this plot to chart onto chart. Okay, so we go to the chart. So just now 0, 0, 30, and then 10, 31.6, and then 20, 33 point, 33 point, not 33, it should be 36, so 36.3. So 36 is somewhere here. And then we have 44, if not mistaken. Go back to the table. 44, 55, 69.5. 44, 44 for 30, 44. And then 55, 55, where is it? Is here. And 69.5 is somewhere here. So that is the maximum. So you plot, you connect all the points. All right. So this is your system curve. So once you have the curve, you need to get the operating point. So the operating point, how do we get? For this question, if you look at the main question, it is stated that the water level at tank B is held constant with a velocity of 0.67 meters per second via an exit pipe of diameter 15 centimeters. So basically from here, you can get the Q because Q is constant. This is a steady flow system. So Q is constant. So Q equals to A exit times V exit. So pi D exit squared over 4 times V exit. So pi 0.15 centimeters squared divided by 4 times 0.67. So what do we get here? So this one is, let me calculate first. This one is 0.01184 meter per second. Meter cube per second, sorry. Meter cube per second. This is flow rate. All right. But on the graph is liter per second. So how do you convert? Go back again for the conversion. So one meter 1 meter cube per second is 1000 liters per second. So if it's 0.01184, therefore 0.01184 meter cube per second is basically, you times with 1000, you get 11.84 liters per second. All right. So your operating flow is 11.84 liter per second. So 11.84 is somewhere here. So if we plot if you want to get the operating point, so just draw a straight line. So the intersection between the operating flow line with the system curve is your operating point. So this will be your operating point. All right. So the question wants to get impeller size. So the impeller size is this one. If you look at on the graph, on the chart, this is the value for impeller size. So since we don't have line here, but the line is very close to 320 millimeters, so you can actually assume the value for impeller size is approximately, so if you look here, I choose 1318 mm. So that's a range of answers, but you cannot write the value to be far from the closest line here. I mean, if you write 300, I think it's not it's incorrect. But if you write 317 or 316, I think it's still acceptable. All right. Then the question also wants you to get the efficiency of the pump. So this is the efficiency of the pump. If you look here, efficiency. So efficiency like 0.75, 0.7, 0.65, 0.6, 0.5, 0.4. And since there is also no lines on the operating point, but you can see that the line here, the trend is like this. All right, the trend is like this. Okay. So we can see that it's in between 0 to 0.4. So I can say that the efficiency is approximately 0.38. So I write it in my answer script. Okay. I write it in my answer script. From the chart, the impeller size is approximately 318 mm, while the pump efficiency, which is this notation or this symbol, is approximately, what is it just now? 38, about 38% or 0.38. All right, so now we have answered question A. And question B wants you to determine the maximum value of Y in order to prevent cavitation. So what is Y? Y is basically the distance from the water surface in tank A to the elevation where the pump is located. So I put it as ZS. Okay? S means suction. Alright? So Y is basically RZS minus Z1. Okay. So to to actually know whether cavitation occurs or not, so you need to have or you need to get the NPSH required. So NPSH required is on the chart. All right. So your NPSH actual from your system has to be more than NPSH required. So how do we get NPSH A? It's from this equation. All right. So we write that equation. NPSH actual from your system is P1 minus PV divided by gamma plus Z1 minus ZS minus HLS, the losses in the suction pipe only. That's why I ask you to calculate the components separately for suction and discharge pipe. So P1 is given 101.3, while PV is 2, is in kilo. So gamma also in kilo, so no need to convert. And then So Z1 minus Zs is basically Z1 minus Zs is basically negative y, because y is Zs minus Z1. So you put here minus y minus HLS. I go back to my equation. It's 123.941 Q squared. 123.941 Q squared. So NPSHA, when y is maximum, when y is maximum, the NPSH A is equal to NPSH required. Alright? Because if it's less, then Y will be more than maximum. So NPSHR, if you go back to the chart, you see here, this is NPSH R. So you see this dashed line? You see the dashed line? This is 3, 2.5, 2, 1.5, 1. So our operating point is in between 0 to 1, but it is more close to 1, and it is also close to the center, which is 0.5. So I approximately the NPSHR is around 0.6. Here. It's between 0 to 1. So, but it's more close to 1, and it is also more close to 0.5, which is at the center. So, from the chart, NPSH R is approximately 0.6. So, 0.6, we go back to this equation. So, 0.6 equals to 101.3 minus 2 divided by 9.810 minus y minus 123.941 Q squared. I rearrange this. Okay. If you want y, so you rearrange so that you get y equals to, and then the NPSHR NPSHA just now we put to the right side. So it's 0.6. So this Q, you use the operating point. So the operating point flow rate is Q operating is 11 point. Just now we get 11.84 meter cube. It's not meter. It's liter per second. Okay, it's liter per second. All right. So remember this equation just now. This one you get from the suction pipe components. It's in meter cube per second. So to convert to liter per second, you have to divide by 1000 squared. So I put here, you divide by 1000 squared. Then you replace the Q with the value of 11.84. Alright, so 11.84 you replace in the, so you replace 11.84 squared. Remember the squared. So what do you get here? If you calculate this, you get 9.51 meters. Therefore, the maximum value for y is 9.51 meter. So y has to be less or same as 9.51 meters. Or to prevent cavitation. So that answers question B. Alright. So that is all. If you have any question, you can write in the comment below. So thank you.